So I guess that I should probably like announce that since Mr. Tim Ansel, that the head honcho of like that the Google project is ready to just actually talk on that the Zoom phone call, so we might as well take an advantage of it and then just actually use that the more ample time for this Google discussion.
Okay, can you hear me okay now?
Yes, absolutely.
Cool. Konnichiwa, that's about as much Japanese as I know. I can't see anybody on the other end of this, but I can hear you. So I'm going to assume that everything is working on your end. If you want to interrupt me, please do. I'm happy to repeat what I said or repeat it slower. I know some of you may not be native English speakers, and I do have a little bit of a unusual accent. And so I'll try and speak more slowly than I do normally. Does that sound all good?
Yes. Speak a little bit louder, please.
Okay. So my name is Tim Ansell, and I'm a software engineer here at Google that leads a team that is trying. We do IC design to make it easier and faster for everyone to do. And the reason that we're interested in this is that Google sees a future where we may have to do more hardware to keep up with the demand of various products that we're developing. I'm excited to see that there is strong interest in this area in Japan. Japan has been traditionally a very strong country in the semiconductor space. And I'm excited to see that you're interested in how we can do all this stuff faster and easier. My team has a couple of representatives that we collaborate with presenting today. The first presenter, I believe, will be my colleague Aaron Cunningham, who is located in Google Singapore and will present on Google's open source hardware strategy. Aaron covers quite a wide range and is the open source expert. My team is very much focused on the silicon aspect. We'll also hear from Rio, who is in the university relations team, I believe, talking about research funding in Japan around the silicon space. We'll also have Johan, who everybody I know calls Proppy, talking about and participating in a panel around open source silicon with members from AIST and the University of Tokyo, and giving a demonstration of some of the cool things you can do with a fully open source toolchain, and hopefully some of the workshops that he has been doing with that group. There's also Mehdi from the University of Michigan, who has one of the most exciting projects that I have seen around trying to automate analog, and how he's really demonstrated portable analog between a wide variety of different process nodes, all enabled through using the open source tools. We also have a representative from Rios Labs presenting how they taped out their first ASIC using the open source toolchain. And we will have a booth in the pavilion which are showing some of the real manufactured parts from our SkyWater Shuttle program. So that is all exciting. Google has been funding a no-cost shuttle program to enable people who are doing open source silicon to get silicon made for free. We originally started with the SkyWater 130 nanometer process technology and have recently added the Global Foundry's 180 nanometer MCU process technology. We plan to expand this program to include more foundries and more process technologies in the coming years. Doing this depends on the success of these existing programs. So one way you can help us have more of these no-cost shuttle programs is by submitting your designs to the program and getting them taped out. So this is a really important aspect, is if you want to see more open silicon, you really need to contribute to the current open silicon. So this is where we're going. Johan on my team is responsible for a very cool site called developers.google.com/silicon, which he'll hopefully show to you, which includes a lot of links and information about how to get involved here. There is, roles and ability to participate is wide open. It's not just for people who are doing silicon courses. We have seen people like high school students, retired professionals, professionals from totally different, industries, and, a huge number of other groups submit designs to the MPW shuttle. So we've seen simple designs, we've seen complicated designs. We very much want to see as many people submit designs as possible. I would also like to give a call out to a very awesome program from one of our collaborators called Matt Ben, who runs a program called Tiny Tape Out. This program allows you to tape out a design in less than 2 hours. And I think Proppy's claim to fame is that he has done a silicon tape out on his phone while traveling to the office through this program. And I think that is pretty amazing that with these open source tools, Johan/Proppy, who is not a silicon designer, could get to a DRC clean result on his phone while traveling to work. And I think this is a really cool example of what openness enables. I'm really thankful that RISC-V came along because it really enabled us to have this discussion about openness in other parts of the ecosystem, like the EDA tools and like the PDK. And it's really exciting to see all the RISC-V designs being taped out through this process, from simple, CPUs to much more advanced out-of-order designs. It's really awesome to see the variety and the innovation that this has really enabled. So that is kind of my 2 cents on why I think it's awesome that we're presenting here at this summit, and what I hope you'll be able to do to collaborate and work with us in this space. I hope my colleagues will give you a lot more details about how to do this and why it's important. And I'd like to thank you for having me come along and give this short introduction about what we're doing and why we're doing it. So I think that's everything from me. I can't hear anything from you if you're saying something.
Yeah, thank you. So I'm just assisting changing the speaker to Aaron. So どうぞ。
Yes, thank you, Tim. This is Aaron, call again from our venue here. So I'm plugging in my laptop now to begin my slides.
Okay, good.
Cool. I'll hand it over to you, Aaron.
Okay, good morning, everyone. Can everyone hear me okay? Yes, okay, wonderful, thank you. Good morning, my name is Aaron Cunningham. I work at Google in our open source programs office. I've been at Google now for 10 years, mostly in the US, but this year I have moved to Singapore, so I'm now based here in Asia, in Singapore, working on open source hardware in our open source programs office for Google. So I work very closely with Tim Ansel and his team. For open source at Google, my team has a very simple mission, and that is to bring all of the value of open source into Google and to bring all of the resources of Google out into open source to share with the world, because we think that's important to collaborate and make progress. So as part of that, Google is a very large company. We have incorporated open source into many of our most successful products. You may recognize Gmail, Android is here, YouTube. All of these are built on top of open source technology, and we understand that continuing to progress those systems is really important to our own success as well. Some very quick statistics from a company level. Google hosts over 10,000 open source repositories for different projects that we work on. We have contributed as employees to over 75,000 projects that are all outside of Google as well. So we believe very seriously in contributing back as much as we can. But today, I'm here to talk specifically about semiconductors and chip design. So many have seen slides similar to this one. This is a graph that is charting the performance of transistors in semiconductor design over many years. And you may have heard claims that Moore's law is slowing or has died. This affects us at Google as well. One of the solutions that we have found for our business is to shift to ASICs, or custom designed processors, to perform work in our data centers. Our most famous example is what we call the Tensor Processing Unit, or TPU. This is a processor that we custom designed specifically to accelerate machine learning calculations, which is how we've been able to incorporate machine learning into so many of our products. Is we've shifted away from generic x86 processing for these jobs to a very specialized system that can perform the same work between 15 and 30 times faster, which is important for us at scale. Also important at a better power utilization as well. We can perform 30 to 80 times the number of operations per watt of electricity that we consume. We've also recently applied this approach to YouTube, which, as you know, is our video sharing website. We have many users who upload video much faster than Google can compress it at scale. So to address this, we've created what we call the Video Transcoding Unit, which is another custom-designed ASIC for us, which performs video compression for the VP9 and H.264 codecs. And this allows us to compress video into different resolutions for sharing to be more bandwidth efficient to users on their phones at 20 to 33 times more efficient. I should point out that this number considers the total cost of ownership of this design. So this includes the design, the manufacturing, and 3 years of operation. Even with everything all combined, it is still at least 20 times more efficient than what we were doing before. So we see there's a lot of usefulness in continuing research in this area. But one of the things that we are noticing, as you may all notice as well, is that design costs are increasing to do this. This is a chart from the US government and DARPA, where they found from their own research that their design and verification costs were significantly increasing. And this is a challenge for them because many of their hardware programs work in very small volumes, which is very similar to academic research. And so one of the things that we are interested in at Google is exploring how we can facilitate more rapid design and iteration in low volumes. Because our TPU and VCU designs are great, but they really only work for us at very large scales where the economics make sense. So we also want to explore how we can make this cheaper and more accessible to everyone else for more research. So, here we go, yes. So this is a very, very simplified view of how we think about ASIC design. But we think about it at Google in terms of three different parts: EDA tools, IP and RTL, and PDKs. So the first, in the realm of IP and RTL designs, we see that there's already a very healthy growing ecosystem of open source IP that is available. Examples here include OpenCores, OpenRISC, RISC-V, of course, which is why we are all here. And we're really excited to see these continue to grow and develop. In the EDA tool arena, we also see very healthy growth and a lot of interesting activity, including open source tools like OpenROAD, K-Layout and Magic, Yosis, the Alliance Coriolis projects. Commercial tools as well are making great progress here in supporting more open source IP and PDKs. Google has some of our own projects in this area as well. These are some of our EDA tools that we work on. XLS is a high-level synthesis tool. We also contribute some system Verilog tooling. Our tool is called Variable, which is a parser that can perform linting on system Verilog code. We've also created a layout generator for creating analog designs called GDS Factory. We use that for photonics research. The last portion we think about is the PDKs. These are the process design kits from the foundries to create designs that can be manufactured at their facilities. Previously, these have not been generally available. If you want access to a PDK, you must first license it or negotiate access with the foundry first, and then design your chip to fit in that foundry. So one of the things that we've tried to do is to increase accessibility to these PDKs. And so our first step was we formed a partnership with SkyWater Technology. This is a small foundry based in the United States, and they agreed to partner with us to release their 130 nanometer process under an open source license. So you can go to this website. This is a GitHub repository, and you can clone the complete Sky 130 PDK with no need to sign any agreements or negotiate any licensing. It is available for anyone to use and incorporate for designing their own chips. This is licensed using the Apache 2 license because we feel this is appropriately permissive to allow multiple businesses to use and benefit from it. And that makes this one of the first PDKs that is both fully open sourced and also manufacturable. There have been open PDKs before, but many of these were predictive PDKs, which used simulation data to get results, but you could not actually manufacture designs that were made using them. This one is fully manufacturable, which we think is very exciting. So with this, we began what we call our Silicon Realization Program, which is to fully test and validate the PDK and the tool chain and to make sure that everything works together really well. We have funded a series of what we call the Open MPW Shuttle program. So this is our multi-purpose wafers. We partnered with a company called eFabless, and they are running a program sponsored by Google where multiple contributors can submit their designs. We combine 40 designs together onto a single wafer and then perform the manufacturing. And then we slice up the wafer afterwards, and each contributor gets a sample portion of chips back that they can then use for testing. The benefits here, it is no cost because right now this is being sponsored by Google. The requirements are that your design is open source. This makes them highly reproducible, which is very attractive for research. And what you get as a participant is basically a RISC-V based management area that performs your basic power control and I/O to the rest of your circuit. And then you have an entire open user project area to implement whatever design you want to test and experiment with. When we started our first shuttle, we received 45 designs in only 30 days, which we thought was very exciting. 60% of these designs were from people who had never designed chips before. We think this is also really exciting as an indicator of what these tools can do when they are more accessible. Since then, we are now through 7 shuttles, and we've done, let's see, almost 500 designs have been taped out so far across 7 shuttle runs over the past 2 years, and we are continuing. Some exciting projects that we've seen. Tim mentioned this one. This is OpenFASOC. This is an analog generator from the University of Michigan. Our colleague Mehdi will be presenting on this, I think, later today. I think Tim also mentioned Matt Venn, who is a collaborator who has created his Zero to ASIC course, where he's actually teaching classes to students who have never designed chips before, how they can design their own chips using these tools. To facilitate this, he created his own system that allows him to take one slot on the shuttle and combine together 16 projects from his students into a single design. We think this is quite clever because where we provide 40 slots for participants in each shuttle, he took one and then fit 16 into that, which was very creative. Taking this to, I think, its logical extreme, he then created tinytapeout.com, which Tim mentioned, and our colleague Johan participated in. They've been able to fit 152 projects into a single slot on the shuttle program. These are, of course, very small, very simple circuits, but for people who have never done it before, it's a great way to get involved and learn. We've also seen some exciting submissions from teams here in Japan as well, including the Jacaranda 8, a PMU, the Marmot SoC, which you will hear about, I think, during this conference as well, and some other projects that are also listed here. Some other recent announcements that we have from Google. This year, we launched our new developer portal. This is at developers.google.com/silicon. And we also announced it on our Japan developers blog. This has more information about how you can get involved, learning material and content, and links to tools for you to begin designing your own chips. We also this year announced our second PDK. We've partnered again with SkyWater to release their commercial 90 nanometer FDSOI CMOS process. This is a great step forward in capability from 130, and we think this is very exciting for further research. And then we also launched a third PDK with our second partner. This year we announced a partnership with Global Foundries, who are beginning this process by releasing their 180 nanometer MCU PDK. This is currently in testing, so we're taking submissions now for our first test shuttle run to work through the process and make sure that everything is working correctly. So if you're interested, we have the link here to find the docs to continue from there. You'll notice all of these are what we call mature process technologies. These are all quite old, quite large in terms of semiconductors. We think that's very important and interesting because we believe that these mature nodes are more technologically accessible. This enables researchers to innovate using well-known techniques on substrates that are very well understood and have been published on for many years, many papers. To be able to make this more accessible and cheaper provides value for that research to continue. And we think the larger ecosystem benefits from this as well. So getting back to the original model that I showed earlier, where we think about our three components, having more PDKs available enables better designs, tool improvements, because each tool will have a new PDK to check compatibility with, and together that encourages more shuttles to continue as well with more activity. Having more designs and IP available really helps us to exercise these open PDKs, to find bugs and to fix them, which then also drives improvements to the tools themselves, which then drive more shuttles. So we're definitely seeing lots of growth across the ecosystem through this higher availability. And then finally, the tool improvements are really important because better tools give you better designs. That allows us to explore things like the portability of designs between PDKs, which is a really exciting area. And all of this together leads to better shuttle results. We've learned lessons through each progressive shuttle program. Each one is better than the last. So we're really excited for this to continue. So I think long term, we're excited to see this kind of approach happen where ideas and designs may begin in a community space, progress through group shuttle submissions, and iterate over time through these open MPW shuttles. As these designs improve, they can mature to then use their own private shuttles for larger use, potentially then adopted by industry for full wafers. So if you're interested for more information, I would again refer you to developers.google.com/silicon. We also have a very active Slack community with over 3,000 members at open-source-silicon.dev. Cool. Thank you very much. Okay, I think that's it. And let's see. Okay, wonderful.
Thank you, Aaron. So we still have plenty of time. Yeah, so if you have a kind of backup or additional slides, so you can talk, if any.
Can I introduce this publication? Go for it. Yeah, and if there's any questions too, I can answer those
So
as well.
before you actually do move into this like a presentation, like that Q&A, I could probably fill in a little bit about this publication called Google Open Source like a Silicon and Asian. I mean, like, you know, like the supply chain in Asia. That's the kind of book that we are going to be distributing this at this conference at Google like booth and also here. And then actually typically like this one, because of that the cost, it actually costs like maybe 500 yen. But today I think to promote and then have you guys to just actually have more interest into this subject, we're going to be distributing it for 100 yen. That's like about 60 cents. However, so please, and within this there's this whole thesis of like Tim Ansell. And then this is a very deep paper, and then it is very sophisticated philosophically and scientifically, hence it is very hard to read. So we created the glossaries, you know, like of terms in at the end of that this whole paper. Hence that, please do, if you are interested, pick up one of the, well, of course this is in Japanese, so I mean maybe might not be that easy, but the thing is, 要するに I have to switch into Japanese. So we try to just actually elaborate whatever that Google is about to do in this brochure. And this can be picked up in a...
Alan,
yeah.
so may I ask some rudimentary questions? Very basic questions.
Yes, and I can try to come up with rudimentary answers.
I understand. So Google TPU or some video encoding accelerator is really good for Google business. Maybe more users are attracted and probably more revenue. So it's good. But except Google application, almost all users. So I'm just wondering, so where does Google make money? In short.
That's a very good question. So to restate the question, I think I would say, I presented earlier that Google is designing many of our own ASICs for scale internally for our use to be more efficient with our resources. Then I also showed that we're sponsoring this open source shuttle program where we are manufacturing open source chip designs for free. And the question is why? Why would Google do this? How are we making money? Very good question. The answer is we don't make money on this part. But by increasing accessibility to this material, the cost of manufacturing decreases. Using a corollary to Moore's law that basically shows that the more practice you have manufacturing something, the lower your unit costs become over time. And so by basically filling the foundry full of shuttle programs to continually run, each run of that shuttle gets cheaper and cheaper. And by filling it full of open source designs, what we do is we're actually fueling improvement to the tools themselves. Because open source tools, commercial tools for that matter, tools do not improve unless the tools are used. And so what we want to encourage is use of the tools. And the best way to do that is by giving people a very easy way to use them to then make designs. So I think that would be the best answer, is basically just to drive use and adoption of the Open PDK, which over the long run lowers our costs for research. Because using mature process nodes, we could take a chip and tape it out through multiple iterations 10 times and have it manufactured, each one getting better at a much lower cost than what it would take to do on a current latest generation node. So I have a question over here.
Yeah, thinking of the PDK tool trends, that I wonder how mature is the open source PDK tool trend for now, because I have heard that in the MPW2 that we are having major flaws such as clock tree analysis, those kind of stuff that makes a completely total failure batch. So how mature is it now? And I want to add up something that there are many RISC-V implementations are written in system Verilog or VHDL. So are these two major hardware going to be supported by open source PDK tool trend?
Yes. Okay. So there were two questions there that I will restate also for those.
Alan,
Yes.
would you repeat the question first?
Yes. Yeah. So the first question I heard was, how mature are the open source tools now? Because there have been issues that you mentioned in the past. The answer is not very mature, but they are getting better. And we think that is the exciting part. So when we ran our first Open MPW shuttle on Sky 130, we found that there were some clock timing issues in the PDK and the caravel harness design. But by running the manufacturing, we found it. And that's why we do multiples of these, is each one gets progressively better. And because it's a mature node,
So basically, we're guinea pigs.
I think we're all guinea pigs in some sense, yes. Yeah, no, but it's completely fair, yes. And that is something that we took very seriously when we found those issues, and we wanted to correct those as quickly as possible. But yeah, I think the answer is it's getting better. And the more designs that use it, the better it gets, which is why we're very excited. And then your second question was, yes, a tool support for both System Verilog and VHDL. I am less of an expert because I'm not a software developer. I'm one of our program managers. But my understanding is support for both languages is improving. It really depends on which specific tools you use, because each one is targeted towards a specific language. But both are very well supported across.
Do you have any statistics on this? Maybe like because there are backwards or many open source RISC-V implementations. Do you have any rough guess on what kind of design is supported? Like NISC-capable is okay, non-NISC-capable is okay, that kind of stuff.
So the question there is, do I have any rough statistics on which designs are applicable there?
Yeah.
I do not in my head, but if you come to our booth, my colleague Johan will have more information there as well.
Your business at Pacifico Pole now?
Yes, correct. Actually, I think it's in that direction.
Okay.
Yeah, yes. But yeah, if you find the Google booth, my colleague Johan is there. He has a microscope set up with samples from our shuttle runs to view. And he has actually taped out designs through the entire process, and so he can talk much more about implementation. Are there any other questions? I will check the Slack on my phone as well.
Yes, we have one Slack question.
Okay, yes, here it is.
Do you see?
Yes, so the question from Slack, from, let's see, Kasahara-san. Do you think about using AI to train on open source or open silicon design data and the results of collation with real chips to create the optimal PDK in the future? That is a very good question. It is not something that we're doing right now, but I would say that's definitely something that is possible. And that's one of the benefits of each of these designs being open source. They are all on GitHub. And so any of us in the ecosystem can go and inspect all of these designs and actually train an algorithm to spot commonalities or flaws in these designs. And over time, I think, yes, that is definitely an area that would be very interesting to research.
Other questions?
Yes, sir.
どうぞ。
So since I've been working in management of PDKs in the Japanese industry, I know there are lots of codes to develop PDK. But in this scheme, so you said the PDK is open source and free of license. So how do you keep the maintenance of this kind of open source PDK? Are there any committee to support, to have a discussion to support the maintenance of PDK?
Yes, that's a very good question. So the question was, traditionally, foundries invest quite heavily in maintaining their PDKs and continually improving them. With the PDK being open source, where is the incentive for that to continue? Is Google helping with that? Is Google paying for it? The answer for these three cases that I mentioned is because they are open source now, yes, Google is contributing improvements based on our usage. We have many academic collaborators in universities who are also creating new standard cells, filling in holes where we find them. But we've also found that our foundry partners are also very interested in continuing to invest because the payoff that they are seeing from these PDKs being available is that their commercial demand has increased higher than what they had before. Where previously some of these mature nodes were seeing less demand for these smaller foundries. Now that they're available, they have more customers than they know how to handle right now, which is a separate issue given the ongoing chip shortage of different mature nodes. But for them, it's a good problem to have. Thank you. Other questions? Yes, sir.
So I was able to just actually evaluate some of your like OpenRAM tool chain using like the Rocket RISC-V processor, and found maybe 3 areas that were like that very interesting. And one is like a synthesis part, logic synthesis. That was like it takes like a huge amount of memory to just actually process that particular part, and then it takes like 3 hours to just actually synthesize each time, each one. And then another thing is that issue with DRC errors and then LBS errors around that, particularly like RAM module. And then third area is that the routing, that the global routing portion of it is a little bit tricky to just actually use. And then we have to just actually iterate like maybe 100 times to just actually get used to it, so forth. But overall, it was very smooth process. But how do you see like the type of activity that you can foresee for logic synthesis portion, and also that DRC errors, and particularly magic around, like the tools, and then another thing is like routing, global routing. We have some specific visions as to how you want to move those maybe 3 areas that is when the logic gets bigger, like the things get tangled up a little bit.
Yes, a very good question. So I think to summarize for those who are joined remotely, 3, from your experience with the OpenRAM tool chain, the things that you experienced were synthesis takes a very long time, lots of memory. You encountered some timing errors and DRC issues. And then what was the third one? Routing, yes, routing as well. And how do we see that moving forward? I think my colleague Johan, you should definitely talk to him as well about, because he has more specific opinions on the tooling. I think we're seeing gradual improvement. One of the demonstrations that he's running in our booth is actually running the tool chain on Google Cloud instead of on a local machine, which allows him to benefit from a much larger scale of an infinite amount of memory and cores, which can make the synthesis part run much faster. In terms of quality of results, I think that's improving over time. I think the biggest value that I see from these tools specifically is it allows academic research to be fully reproducible. Because now, if a researcher publishes a paper on a design that they've created, it's very difficult for other researchers to accurately reproduce it, to conduct their own validation, to support the claim or disprove the claim, or more importantly, to then build upon that research to make continued improvements. Because to do that required you to negotiate access to all of the exact same IP, which is not always available in every region or at every university. And so even if the current results are not optimized and maybe a little bit difficult to use now, the important thing is that they are consistent and that they can be consistent anywhere around the world, used by any user. And that I think their quality will improve over time as adoption increases. So, were there any other questions? Yes, one here.
Well, I have a question. Are you going to plan to add more package about system level support? Because uses and some other tools in OpenRAM cannot support system Verilog?
Yes. So the question was, there are portions of OpenLane and Yosis that do not support system Verilog, and are we planning to add support for those? The answer is I think so, yes, but I would need to confirm with my colleagues to make sure that I do not give the wrong answer. So yeah, I would say if you come visit our booth and ask, we can confirm that for you. And then we had another question in the back. Yes, sir.
I have two questions. The first one is regarding the FDSOI. When will that be available? That is the first question. And the other question is how the PDKs are different. Right now we have SkyWater 130, and recently we have Global Foundry 180. How those PDKs are different? If I have a SkyWater 130 design, how can I convert the design to the Global Foundry?
That's
And the names are the same, and the inputs in order, parameter names and parameter meanings. How about those differences?
Yeah, very good questions. So the first question was, when will the 90 nanometer FDSOI shuttle program be starting that I mentioned in my slides? The answer for that is we do not know yet, but as soon as possible. We were hoping to have one started this year. We're still waiting on some things to set up with the foundry for this to happen. It may not be until after January, but the answer is very soon. We're working very hard on having the 90 nanometer PDK ready and available to begin manufacturing. The second question you asked was, what is the difference between the PDKs? How similar are they? If you design something at Sky 130, can you very easily port it over to Sky 90 or Global Foundries 180? The simple answer is they're not very similar. Each one is very unique and specific to that foundry's capabilities. They do not always use consistent naming because traditionally PDKs haven't been open to the public before. So there really has not been any reason to use consistent names. Each one has always been its own unique process. But I think that's one of the things that we are excited to explore is now that we do have two PDKs available that we can look at side by side, can we improve the tools such that designs could be ported between them? Right now they cannot, but we think that in the future that would become a possibility. Cool, thank you. Yes, one more question.
So that means that do you have a kind of opinion, the kind of PDK is going to also some kind of standardization in the future?
Well, that's a very good question. So does this mean that there could be some kind of standardization of PDKs in the future? I do not know. I think that would be very exciting, but maybe in a few years.
Yeah. But it could be kind of ideal, the situation on the OpenEDA and OpenPDK environment, right?
Oh, absolutely, yes. I mean, I think that could benefit all EDA tooling, not just the open source ones. What we're interested in really doing here is improving the entire EDA ecosystem. And we think the first step is just having these PDKs more available to make it more accessible for research. Cool. Wonderful. When is lunch?
Yes, please give me 3 minutes for the information. So, okay, so thank you, Alan.
Cool. Thank you, everyone.
Very good presentation.